Welcome back, everyone, to the Open World Lifelong Learning course. We're actually in our final session today, so it's been a long ride already, and we're in week 12, and we're going to do a little bit of a course wrap-up, talk about the frontiers. Even though we've talked about a lot of frontiers already, we'll talk maybe about even more frontiers. And if you do have any questions, if you are participating in the live stream, then you are also encouraged to ask as many questions as you want about today's session, about the entire course, either at the end or all the way throughout today's lecture. Of course, if you're watching a recording, feel free to comment on the YouTube chat and we'll see if we can get the questions answered later. As a small word of caution, it is about 40 degrees Celsius right here, over 100 degrees Fahrenheit, so I'm basically melting away, but I hope my brain is going to function enough to give you a roughly 1 hour lecture nevertheless. So let's do a little bit of a wrap up of the course. For those of you who have already watched all of the course, and for those who are just for some reason watching the session for the first time, this is essentially a summary of what we've seen so far and what you can still learn. So we've started with the question, basically asking ourselves what we think machine learning actually is. And we started from this very basic sort of idea, not basic in the sense of that there aren't many steps, but basic in the sense of that it's a simple or supposedly simple recipe in the form of having a bunch of elements in a sequence coming from defining an objective to collecting some data, preparing the data, selecting the algorithm, etc., all the way to this very common notion of train validation test splits. And we started this entire course with the question, if we want to do something like lifelong or continual learning, is it as easy as just basically iterating over these steps? And we've come fairly quickly already in the first lecture to the conclusion that is possibly way more complicated than the typical train validation test split. So what we've seen in the very first lecture as an outline of the course was this diagram. And when I've introduced it, I've mentioned that it's basically putting these steps seen on the former slide into a circle. You can again see the prepare data to the selection of the model, the training algorithms now on the inner circle here. And we've said that the gray boxes are the questions that you typically ask yourselves independently of what you do when you do machine learning per se. So we've said that on the data box around on the top right of the circle, we would ask ourselves questions surrounding, for example, how much data do we need? Is it redundant? Is there enough diversity present? How do we need to clean it or pre-process it? And then we've asked ourselves questions on what's a suitable model architecture, which inductive biases do we need for a task, etc. But hopefully during the course, we've realized that a lot of these questions are somewhat individual questions in the sense of that they get addressed in almost in isolation, I would say. And we've then delved into more or less 12 weeks or 11 weeks, if you discount the introduction, 11 weeks of figuring out the interdependencies and the synergies which are displayed in the orange boxes here. So I hope that after listening to the course, you are at least gaining a little bit of an understanding of how important it is and also maybe how challenging it is to bring the elements together and why it's really necessary to do so in the future. So we've had some of the examples, which I'm going to delve into further on the next slides, on the different sort of orange boxes. Here as an example, if we are sticking to this data perspective, if we do in fact are interested in continual or lifelong learning, we'd no longer just be curious about the amount of data that we need, but we'd also maybe ask ourselves the question of what data do we select next in the future, which we've seen in active learning. We'd ask ourselves maybe about how order of the data influences our final performance or our intermediate performance, e.g. in the curriculum learning setting, alongside other questions such as the task similarity, whether there are noisy streams, and what types of distribution shifts we may potentially encounter. So really what we've done in the lectures is we've kind of gone through these boxes in orange from top right, more or less in a sequential order to top left, excluding potentially the entire versioning question, but looking at more or less most of the elements in these orange boxes. We've spent some time on evolving test sets and the question of open worlds. And today we're going to look at some of the frontiers which we have encountered there already and some of the frontiers which we are maybe yet to encounter, one of them being the deployment box on the top left, on the bottom left. So before we get into these frontiers, let's figure out quickly what we've actually talked about, what each and every individual lecture was about, and what each and every individual lecture has actually taught us. So I encourage you very strongly, if you are watching the live stream, to just participate in the chat and just throw in things that you think you've learned. And in particular, I encourage you to throw in things that you believe are frontiers. Because doing today's lecture is actually a bit interesting in the sense of that it's called Summary and Frontiers. But if you've really been following the lecture and if you've been following the entire course, then you will have noticed that almost every individual session was more or less already a frontier in itself. So what do I mean by that? What I mean by that is if you recall, and again, I encourage you if you're watching a recording to just stop now and recall this for yourselves, that each and every one of those boxes here on the slide, such as transfer learning, has a particular way that we understand it right now. It has a particular maybe definition even, but it has a lot of open frontiers that are yet to be considered. So I'll start for you on the example of transfer, and maybe we can just go through these boxes a little bit step by step and just figure out what we think we already know, what the perspectives are we've encountered, and where the frontiers, at least partially, still lie. On the transfer box, this would be all about knowledge transfer. And so what we've talked about there briefly were the ideas of coming from the more formal definitions of transductive transfer and inductive transfer, and we've then figured out how this relates to concepts like domain adaptation, few-shot and zero-shot learning, and then we've asked ourselves what it actually means to transfer knowledge. We've quickly come to the conclusion, or maybe the insight, that in machine learning, transfer is typically thought of as knowledge in the form of parameters, especially if you talk about neural networks and deep learning. We'll circle back to this later in today's session to just briefly recall what knowledge really is or what knowledge really could be. So in that sense, the frontier in transfer is still that we're lacking an understanding of when to transfer, when not to transfer, what is really transferable, coupled with this idea that especially deep neural networks and a lot of machine learning, present machine learning systems are quite opaque, they're quite black boxy, and in particular in the sense that knowledge is actually more than just parameters, as we'll see later today again. After we've then briefly talked about one session about transfer in the positive sense, we've also talked about transfer in a negative sense, in the sense of that we're forgetting knowledge by overriding parameters. We've spent 2 sessions on this in what a lot of people would call continual learning, but I hope that in this course I've at least opened your eyes a bit that continual learning is a tough thing to define because it's not just about catastrophic forgetting. In this catastrophic forgetting perspective, however, we have encountered 3 different views of how to address catastrophic forgetting to the best of our present understanding. This has been, on the one side, the idea of regularizing parameters in the sense of let's discourage deviations from the parameters that are very task specific, meaning we would identify the parameters that are really important and make sure those don't really change and only allow changes in the parameters that are maybe less important for a particular task. We've said that this is related to what people call the stability plasticity dilemma, or the stability plasticity sensitivity trade-off, where it's basically all about how much do you allow change and how much do you discourage it in a limited capacity setting. Speaking of limited capacity, we've encountered a second paradigm, which was essentially on this idea that we could also just add complexity to our model in the sense of we'd add parameters, we'd add function, we'd dynamically adjust our models in a sense of having more modular style architectures. And lastly, we've talked about the idea that maybe knowledge is not just about the parameters, maybe it's also partially about the data that we've learned. So we've taken a look at rehearsal in the sense of either storing subsets of the initial data set, such as a formal core set, or we've talked about the idea that you could use a generative model to replay some of the examples from previously encountered data distributions. Now, like I said, if you feel like you want to interrupt me at any time with a question, feel free to do so today. I hope that today is really a bit also about questions if you have any, and not just me talking about the summary, but feel free to also just listen to my summary first. So after we've talked about knowledge transfer in the positive sense, we've also talked then about knowledge transfer in the negative sense, like negative backward transfer, i.e. forgetting. And we've moved away a bit from continue learning from the views of parameters and forgetting to data a bit more. And in this perspective, we've talked both about active learning and curriculum learning, not in this order, but eventually. So in active learning, we've said that what about not only the question of do we forget our knowledge when we continue training, but also what about the maybe reverse question, what is the data that we should include next? And in there, we've spoken about active learning, which was really all about the setting, usually in a quite closed world scenario, as I'll summarize in a second again. So the scenario that is typically considered and that we've encountered in the course was that we would consider like a pool of existing data, and this pool would grow by querying into some streams or an unlabeled pool that exists somewhere else, like the internet, and figure out which of these instances to include to grow this pool that we have. So in a sense, it's not really a continual setting maybe necessarily because we didn't worry about the forgetting question simultaneously, but it's continual in the sense of that it trains over time under the assumption that typically our data set grows. This was, in a sense, all about the question of importance. Importance in a way that we've asked ourselves, what is the important data to include? What is the data to include that maybe minimizes our loss the best? So if we have a choice of 10 data instances to pick, our goal was formulated such that we pick the element that lowers the cost, the loss in the best possible way. We've also seen maybe a complementary or quite different take on this in the curriculum learning setting, which is in a sense quite similar to active learning because it also grows the data set over time, but it grows it from a different perspective by asking the question of difficulty rather than maybe of what is the element that lowers the cost the most. So we've spoken about how a small and easy subset could be something that we maybe start with, and how we can grow the subset over time to an ever larger increasing dataset size that becomes more complicated, somehow coming from this notion that that's also how humans are supposed to learn. And in there, we've then asked ourselves two questions, which were all about, first, the question of how do you define difficulty? Like, what is the notion of difficulty you have? What is an easy subset? What is a hard subset? And then we've spoken about the idea that we'd also additionally need to figure out the pacing, meaning how rapidly we introduce new examples. Do we converge first? What's sort of the training strategy over time that we have? So I've skipped the frontiers a bit, but let's circle back to them before going on. In a sense, the frontiers here were also always present. In forgetting, one of maybe the big frontiers is that there are these three perspectives on regularization, dynamic architectures, and rehearsal, and it's a bit unclear perhaps when to use what, which is something what we've talked about a lot in the evaluation scenario. It's unclear not only when to use what, it's also unclear when a particular strategy may be effective, especially if you recall that a lot of the algorithms we've seen were quite particularly tailored to a specific scenario. And what I mean by that is if you recall, for example, the iCarl algorithm, it's a great piece of a system, of a software piece, but also at the same time, it's perhaps a bit limited in the sense of that it's very tailored to a supervised classifier setting. In active queries in curriculum learning, we've had a bit of a different challenge, which was maybe also a bit on the question of what it is that we want. So do we actually want to have these subsets grow according to difficulty, or is it that we want to grow these subsets by something like an importance value? Do we want both? Do we want a mix? empirically somehow, if you take a look at the final outcome, you're actually maybe interested in something similar. So there are strong relations. And there we've then seen that it's quite tough to actually decide on the measure on which to base this query on, or on which to base this difficulty. So we've seen various empirical results on the correlations. We've seen some more theoretical results, such as the idea of version spaces in active queries. So the idea that we can reduce the set of possible hypotheses in a model, but it's never really there wasn't this like one fits all solution yet. And particularly if you think of active queries, we've said that a very popular strategy is to use heuristics like an uncertainty measure on top of the predictions or just the prediction value itself, where we've very rapidly seen that this can work extremely well in particular cases, but it's not something that's generally robust when we move away to something called the open world scenario. So what we've done is we've said that all of these sort of paradigms exist a bit individually, and they have their purpose to exist because we need to find out like nits and bits of the different techniques. But there is an additional challenge in puzzling them together because the perspective that we have then is fundamentally different. And it's fundamentally different already by acknowledging the fact that a lot of real world scenarios may be open world. And so just as a brief reminder for you, what that meant was that if we have a active learner, for example, or a catastrophic forgetting investigation, we typically know precisely where our test set comes from. We assume it's somehow similar to the training data set. We assume it comes from the same distribution. If it's a continual setting with multiple tasks, then we still know that it's a test set that comes maybe from the second, from the third task, and so on. But in a real open world, maybe you can imagine that a lot of the data that you will encounter is not something that's at all accounted for. So we've talked about the idea that there are knowns and there are unknowns, and in particular, we've talked about the idea that there are known unknowns, so things that we know we don't know, but there are also a lot of unknown unknowns, meaning data that we can encounter which we have really not anticipated ourselves. And so we've said in one of the more late lectures in the course that it's an interesting idea to start puzzling the pieces together in something called like an open world learner or a lifelong open world learner. The ideas of the initial open world learning, or one of the initial open world learning works, was to, in essence, combine really the gists of open set recognition, like this idea to recognize when something is inside your closed world or outside. So identify what is known, identify what is unknown. Then on top of this, kind of combine it with this active learning idea, meaning you create a pile of like novel unknowns, and there you figure out which are the elements that you would like to maybe annotate or just include in your set to continue training on. And on top of that, you'll then put on some incremental learning strategy, be it with or without avoiding catastrophic forgetting, depending on whether you accumulate the data set, to sort of have a training cycle that incorporates these perspectives into like one single system eventually. Already there, we've said quite strongly, or we've emphasized that many of the papers, many of the current works are in fact called towards already in the title, suggesting that open world learning as a concept is fairly, maybe not novel in the way it's formulated, but fairly fresh in the sense of being implemented in modern systems right now. So there's lots to be done. And in that sense, the title of the lecture itself, Open World Lifelong Learning, is the frontier already. To conclude the summary a bit before we go on and maybe summarize in a different sense and go on to frontiers, we've talked about evaluation, soft and hardware, and we've had various guest lectures, 2 guest lectures to be specific here. So in the evaluation setting, we've mentioned that already the train validation test scenario is something that's quite tough sort of to think about because we need to extend it. But then we've realized, hopefully, that if we extend it, in fact, across various dimensions, it becomes increasingly difficult to evaluate. Not only because the number of measures that we could be interested in somehow explodes, but also because maybe particular applications kind of warrant the existence of particular ways to measure or particular measures to emphasize. So we've talked about various of these measures, we've said why it is important to take a look at them, and we've basically left it open a bit in the sense of that there's no one set to rule them all. But I hope I was able to tell you that we should be transparent about the ways that we evaluate and acknowledge that there are a lot of factors that we should be considering. And if we're not considering them, we should at least be open about why this is not the case. On a similar view of limitations, again suggesting already how the course itself had a lot of frontiers, we've talked about soft and hardware. And whereas we've had a really interesting guest lecture on Avalanche and how we can construct, in this case, PyTorch software to address continual learning, how to extend our current software tools, we've also talked about a bit of a historical development of soft and hardware, and have then ended on the note that it has not only enabled us to create machine learning systems, it's perhaps also restricting it a bit in the sense of that we're very focused on a set of tools, on a specific set of tools, that it becomes perhaps a bit tougher to now branch out again. And so finally, as a rough summary of what we've seen, and transitioning to the frontiers a bit, we've really encountered many frontiers already in each and every one of the individual lectures. So my goal in the entire course was that in each of the individual lectures, there was something to learn in the sense of that it's a perspective that is more or less agreed upon in the literature, but also directly highlighting the challenges that are still open, the frontiers that we still need to take a look at, especially when it comes to branching out of these individual paradigms and trying to connect them towards something like a open world learner. One of the central questions in that sense then could really be summarized about the frontiers in terms of what's the trade-off. Like how much do we value the whole in the sense of really investigating large-scale open world learning systems, and how much utility do we still have in evaluating like the individual niches? I think on this statement, it's quite important to actually do both. And I hope that I was able to convince you of that there's both value in taking a look at, for example, active learning individually and trying to figure out the perspectives, or addressing catastrophic forgetting individually to just overcome this challenge. But there's also somewhat of dependencies, synergies, and like complex interplays that become really important. So ideally, if you have been following this course, or if you're still about to follow the remaining lectures in the course, the left diagram, or rather the elements on the left diagram, are now buzzwords that you can somewhat make sense of, because each and every single one of these buzzwords has been a topic in one of the course's lectures. So like I just said, one of the really interesting questions is how much do we study overall systems and how much do we study the specifics? And in a sense that this also comes down to the question of how much do we emphasize applications versus how much do we emphasize maybe theory and the fundamentals of machine learning. Rather obviously, I think it's extremely important to study both, but it's maybe not so clear when it comes to applications of when we study what, in the sense of, if we think back of a diagram that we've seen on the left-hand side when we've started to talk about open world learning, we have mentioned that there is somewhat of a transition between scenarios where we believe a closed set assumption, in the sense of the test that really corresponds to the train set will never encounter something that's, sorry, I didn't want to say corresponds to, but is related to the train set like quite closely, that this is a reasonable assumption maybe in some applications, like think of you're in a warehouse and there is a certain limited amount of items you can see, the lighting is always the same, the world doesn't really change a lot, but it's not so clear like where exactly the transition happens to when you may need to think of open world scenarios and worry about particular types of robustness. One take that we've had on this is that perhaps it's not really that important to pinpoint this extremely precisely in the sense of trying to arrive at the definition, but maybe it's a bit more about really figuring out the nuances that make up a specific paradigm that people talk about. So maybe it's more about the differences in how we set up and evaluate, rather than saying that one is a more correct version of the other, or that one is a perfectly suitable scenario in a specific case. So at the very beginning of the lecture, we've seen like this very ginormous diagram on the right, and I hope that when we've gone through all of the individual lectures, we've actually been able to now make sense of the individual connections here. So on the example of transfer learning on the right-hand side, we have, for instance, seen the definition in lecture 2 of what transfer learning is. We've said that transfer learning, it's kind of a very particular way of thinking of knowledge transfer, in the sense that we start with a source domain here being defined by a tuple of a data distribution and a task. And then from the source domain, we leverage the knowledge, often the parameters, to accelerate and improve training on a target task, a target data distribution. We've said that typically we would only then care about how much we accelerate or improve on the target. And one lecture or two lectures further down the line, we've said that one of the key differences, for instance, when people would call it continual learning, would be to also maximize the performance on all tasks in the sequence, meaning preventing forgetting on the source. Similarly, on the arrow to the top right, I hope it now became more clear throughout the course that if we talk about few-shot learning, we essentially mean a transfer scenario where the transfer now is limited in a different perspective of having access only to a few potentially labeled data instances. So it's, again, a transfer learning scenario, but you just have less target data available. And so in that sense, if you start looking at this diagram now, I hope the definitions, the loose definitions, because they're not mathematical definitions often, and the particular ways in which setups are being thought of and evaluation is being conducted is becoming more clear. We can look at the similar perspective here, where, for example, on the bottom half of transfer learning, we've talked about domain adaptations. That was precisely this idea, the difference between inductive and transductive, where we've really said that when people call something domain adaptation, it's all about the fact that it's a transfer scenario where a particular one of the two elements basically changes. In this case, the data distribution drifts, but the target task actually stays the same. So it's, in that sense, a subset of what transfer learning overall is. And in that sense, maybe transfer learning is a subset of continual learning. On the left-hand side, it's quite similar with active learning and open world learning. So in active learning, we'd said we would like to query data to include into future training. In open world learning, we said we also would like to query data, but we'd also like to first detect unknowns before we do that. In curriculum learning, we've said that it's a different form of thinking about it, where we also query data, but by basically assigning an instance a difficulty measure, either in a preconceived notion of difficulty or on the fly through some ways of, for example, self-pacing. Now I'm going to proactively ask the question here, is it even possible or desirable to strive for a unified definition of, for instance, lifelong machine learning? I'm saying this because in lecture 2, some of you have already asked what is continual learning, what is lifelong learning, and even what is few-shot learning, etc. And whereas I believe personally that it's possible to give you a definition of few-shot learning and transfer learning like what we've just seen, it maybe becomes quite perhaps even impossible to do so for lifelong learning, at least if you think of a really, really comprehensive definition that encompasses it all. So we've started in lecture 2 with a formal definition of lifelong machine learning that's more or less quite popular, at least back in the day, that really hasn't had a lot of information. It has just said the system has performed n tasks, and when faced with the n+1 task, it uses the knowledge gained from the n task to help the n+1th task. Already in lecture 2, before listening about all these perspectives, we've concluded ourselves that while this definition has some interesting elements in terms of leveraging the knowledge gained from previous tasks, it leaves a lot of room for exploration and a lot of room for ambiguity. So at the end of the second lecture, we had in fact followed up with a more, maybe slightly more precise, but particularly more long definition of lifelong machine learning. And the interesting part was here more or less concentrated around the center, where it now added this notion of the objective of LML is usually to optimize the performance on the new task, but can optimize any task by treating the rest of the tasks as previous tasks. So it was about a knowledge base, or the concept of a knowledge base, maintaining the knowledge learned and accumulating it from learning the previous tasks. And whereas this definition has in fact become longer and maybe slightly more comprehensive, I think, circling back to my question of how useful it is to really pinpoint a precise definition of lifelong or continual learning, we really have to ask ourselves the question of, is it possible to contain everything we've discussed in here? And is that something that we want in a sense of a frontier? So this precise definition here, it does in fact contain some things we have not discussed yet, especially in the last sentence, like the updating can involve inconsistency checking, reasoning, and meta mining of additional higher level knowledge, which is something we'll see in a bunch of slides. But at the same time, it does not mention at all things that we have learned about, such as active data queries, difficulty, and like the concept of curricula. It does not say anything about the model architectures or inductive biases, dynamic models, etc. It doesn't even account for the fact that testing could be in an open world scenario, and not to say, of course, various like software, hardware, memory, compute constraints, and so on. So imagine if we were to now start putting in all of these concepts, and I understand this may be a subjective take, which not everyone agrees upon, but at least in my view, I think arriving at a definition of lifelong machine learning that really encompasses it all and leaves no room for ambiguity is potentially ill-posed. In that sense, there is much to still be investigated and connected, and even beyond the topics that we've explored in the course, but also especially in the topics we've explored in the course. In retrospect, I think we can ask ourselves one question, however, and it is that a lot of the questions we've been asking really evolved around the idea of data and task heterogeneity at the center. So surely when data is distributed independently, identically, and it is homogeneous, then the world's kind of, I wouldn't say easy, but definitely way more easy than the ideas that we've talked about in the lecture. A lot of the problems or a lot of the challenges really started arising when we have in fact accounted for data and tasks being able to drift and change. And so as a frontier, to give you a bit of an illustration that this is not something that's extremely particular to the things we've talked about in the course, I want to give you one example that initially may sound like it has very little to do with what we've talked about, but I hope I can convince you that the elements you've encountered in the course are actually applicable to a lot of things you'll see in machine learning. So the particular example I want to mention here is the idea of federated learning. And so federated learning comes from what you might think is a very different perspective. It is the scenario where you have different databases, here database B1 to BK, and you have something called a local client, basically being synonymous to a physical or usually physical device, like a mobile phone or a server somewhere. All of these clients contain a model, and these models are trained on their respective datasets. But of course, the idea is that you'd somehow like to share the knowledge, and you'd somewhat maybe like to even have a centralized server that acts as a component to like integrate all of these clients and communicate back to them. So in a kind of traditional federated learning setting, what you do is you'd have 4 steps in which you could do this without maybe necessarily violating the data privacy, although I'll have a comment on this in a second. So what you could do is you could train each model for a bunch of steps on each of their individual databases. And then rather than communicating the data, you could send, for instance, encrypted model parameters or encrypted gradients that you could then aggregate on the server, for instance, by simple averaging in the easiest fashion, and then sending sort of the accumulated update back to tell all the models of how they should change. In that sense, you're communicating something, but you're communicating parameters or gradients and not really necessarily the corresponding data that might violate privacy. Now, I said there is a small star that in certain particular scenarios, if you're an attacker and you attack the gradients that are being communicated and you have the entire trajectory, it's quite likely that you can actually also reconstruct what data it has been trained on. There are, of course, mechanisms to put on top, but let's not mention them here. In a sense, it's a scenario that comes from the idea that you have physically distributed data sets and devices that you may not want to directly couple to each other. You may not want to share the data. So it's all about having a lot of clients and models communicating updates instead, and then being worried about communication rounds, like how many times you communicate. And so we can ask ourselves the question here, although perhaps the motivation is very different from the motivation we've had in continual learning, where it wasn't so much about privacy and how we can leverage data that someone else has access to. It was also perhaps in a similar scenario in the sense of that we also have different databases. Now, we didn't have these databases in this sense of horizontal distribution, but we've maybe had databases in the sense of a sequential process. However, we can think of this perhaps in a unified way, and I hope I'm not going too out of the box here and trying to convince you of that. But we can think of federated learning also in terms of three scenarios. So there may be a scenario where the data is distributed in different so-called silos or databases, but they contain the same feature space and just different samples. So if you look at this very bottom left plot, what is meant by this sort of horizontal federated learning is that if you have sort of your samples on the y-axis and features on the x-axis, that you have drawn different samples from a data set that reside now on these different client databases, but they all share the same feature space. And of course, then if you think of this scenario, you can imagine the opposite, where if you have multiple databases, perhaps you have even similar samples, but the features that you have in the database are different. Naturally, if you want to maybe have a practical example for this, you could maybe think of a hospital scenario where either you have various different patients with the same sort of features that you acquire, but maybe also you could have the same patient and you could have different kind of methods of acquisition that give you different information about the patient. And so if you think of both these sort of horizontally and vertically partitioned federated learning, where in one scenario, the same features are contained but different samples, and then the other scenario, different feature spaces are contained on the same sample, it's not that far-fetched to also think of a kind of transfer scenario, which is really then that both are different. And if we think of the case that both are different, then we may also ask ourselves then, is this really all that different from this transfer learning scenario or this continual learning scenario? Maybe not in the sense of that it's distributed through time necessarily, but it's distributed across physical space, but encountering the same challenge of data distribution changing, drift basically happening, just not over time, but in a physical space. So we could ask ourselves, are federated and continual learning then in their challenges all that different, in the sense of that it's going to be a lot about how can we accumulate our knowledge, how can we aggregate our knowledge without having to worry about different forms of interference. Especially if you think about maybe combining this, and I think this is the part why continual/lifelong learning is so interesting, is because it's not something that's completely sort of theoretical, but it's really something that becomes practical if you think of realistic scenarios. So there was a recent paper which is quite amazing in the sense of even coupling federated and continual learning by motivating from this hospital scenario where it's not only in fact about like horizontal or vertical federated learning, but it's really about both. And of course, in this motivation of the paper here, it's coming from a crisis, a pandemic. We're still all in, unfortunately, even at the point of recording or live streaming this talk, which is the COVID pandemic. And so you may know, if you've been following, and you've likely been following the COVID pandemic, that certain variants have originated in certain parts of the world at particular points in time, and then they have crossed into like other countries over time. So in that sense, you have both the scenario of that different hospitals may have very different data, but also you have this problem that different variants of the same disease or similar diseases arrive over time, meaning in fact that your data is both distributed like physically in terms of the world, but also in terms of time. And so in that sense, you may need both, and you can ask yourself now, if you think of federated learning, you can literally, I think, go ahead and ask yourself every single individual question we've been asking ourselves throughout the course in this distributed scenario now. So you could think of a scenario where you have the data set, and of course you could treat it as if this data set was identically independently distributed like across sort of very different clients, like you just uniformly subsample the data set, partition it. But you can also think about like these various mixtures where maybe on client one, you first have a data set one, and on client two, you do in fact have some sort of variant, a different subset of the same data set. But maybe also at a different point in time later, when a new COVID variant, for example, arises, the data set on client one is in fact very different from the types of diseases it has or the variants of the disease it has than the client two. So in that sense, you can ask yourself the same question on knowledge transfer we've been asking ourselves here in as illustrated on the right diagram, where maybe if you have like a target client, a target model that you're currently interested in, and you want to figure out what is the knowledge you can kind of now transfer from different clients and their time trajectory. There are some like assisting clients that will reinforce your knowledge that are positive in that sense. And there are some clients that are going to interfere, especially if you just naively average and disrupt your current knowledge base in a similar sense to the questions we've been asking ourselves in terms of forgetting, which is one form of catastrophic interference. So as an example, this particular work I'm illustrating on the slide has in fact done that. And what they have done is they've taken a look at the federated learning framework from this averaging perspective that I've illustrated on the first federated learning slide, and has put one of the ways to prevent catastrophic forgetting on top, namely the one of taking a look at models from like a regularization perspective, from a masking perspective, in terms of identifying the important parameters and making sure those don't change. So the particular idea here is that we can really start applying what we've learned like in the course here on modular architectures, where we could say that we decompose, for instance, the parameters into something like a generic set of parameters that each client benefits from, and a subset of parameters that are like really task specific, that have a particular like task specificity in like an importance value, that are maybe only important for a particular client, and only a particular client should not forget if this is like a scenario that one hospital encounters a lot and others do not right now. And then of course we can then share these task adaptive parameters to other clients as well if it turns out that you need them in a new task, and so on. And so perhaps it's a similar question with just different trade-offs in mind, but quite clearly, at least in my vision, it's a lot about like data drifts, data distribution changing, and tasks changing over time or over space, with different trade-offs maybe in mind if we take a look at it from a distributed/federated perspective, such as communication cost. But overall, we're back to like this frontier that evaluation assumptions and setup assumptions are really something that, at least in my opinion, we need to talk about way, way more in machine learning. it's quite opaque a lot of times when you read a paper to really figure out what it is precisely that is being done, in particular when we talk about anything that moves beyond a very traditional train validation test split, like a static train validation test split. So again, just to iterate, perhaps there's no such thing, in my opinion, as like a single set of valid assumptions and ways to evaluate. But what we definitely do know, hopefully from the course, is that there's more to machine learning than just a single number. There's definitely way more to machine learning than just a single number in continual and lifelong learning when we go into any of the scenarios that don't just evaluate on a simple train validation test split. So there are a lot more frontiers that we could talk about now. In fact, I think it's almost endless. Like we could talk about meta online learning. Unfortunately, I initially promised that we would have a meta learning lecture in this course. We've then replaced it due to feedback with a lecture on reinforcement learning instead. So meta learning in that sense, like learning to learn as a framework on top, is just mentioned then here as a frontier. There are algorithmic like system solution that are literally a frontier in the sense of that, as I've said earlier, a lot of the content we've seen has showcased nice solutions, but solutions that are perhaps not agnostic to the level of supervision. Like they don't really work coherently across supervised, unsupervised, and reinforced learning or self-supervised learning. They're maybe more specific to a particular scenario, which, as I've said, may be okay. But of course, on the flip side, maybe if we do think of like general artificial intelligence at some point rather than just machine learning, maybe we would like mechanisms that are more encompassing. In particular, if we start thinking about important topics such as causality. So, of course, this entire course has been about machine learning, but we shouldn't forget the perspective of the more general AI on top. And so causality, for example, examining really like the cause effect scenarios rather than just correlations is something that is a frontier that is luckily, really fortunately, gaining attention again in the last couple of years. So in that sense, I want to mention a final frontier and then just have a bunch of slides to explain why I would call this a final frontier, which is, in a sense, taking this course and almost doing a second version of it, but crossing out lifelong open world machine learning by replacing the machine learning part with maybe something that I'd refer to as hybrid AI or just AI in general. Why am I saying this? I'm saying this because already in lecture 2 at the beginning, I warned you when we talked about transfer learning and sort of the transfer of knowledge, that knowledge in fact is a lot more than just parameters. And of course, in machine learning, it's very convenient to think of knowledge as parameters, but parameters are just one particular type of knowledge that we may or may not care about. I've already said earlier that exemplars, in a sense, or like stored data instances, could also be one form of knowledge. But naturally, there are various things that we may find interesting to store in a knowledge base for a lifelong learner. For instance, we've had this example of never-ending language learners and the never-ending image learner that I've mentioned at the beginning of lecture 2. And I've had it on 2 slides, and then immediately I have said that it's too complicated to think about now. Let's do all of the other lectures first and then circle back to it. So I'm coming back to this promise a little bit now as the final thing in the entire course, to circle back on the explanations of the never-ending image learner and the never-ending language learner, to tell you about why we've waited up to the 12th lecture to talk about it really in more detail, but also why although it's 10 years old, it kind of shows us a particular frontier with respect to hybrid AI. Why am I saying this? I'm saying this because if you take a look at what NEAL, so the never-ending image learner, let's start with that first, what it extracts is, it's 5 things. It's object categories with bounding boxes, because it's a visual learner. It's labeled examples of scenes. It's examples of attributes. It's visual subclasses of object categories. and its common sense relationships. So we can already see here that it's way more than just parameters. In fact, there are different kinds of knowledge that is represented. In particular, things like common sense relationships that up to today we've not really even talked about in the entirety of the course, because it's something that maybe machine learning from a purely like numerical optimization point of view isn't really concerned with. So I think it's interesting to look at the definition of what they say is in fact knowledge. And let me just read it out to you as a quote. It's saying we define visual knowledge as any information that can be useful for improving vision tasks, such as image understanding and object scene recognition. One form of visual knowledge would be labeled examples of different categories or labeled segments boundaries. Another example would be relationships. So the particular definition of the not of their use, like practically employed knowledge base, is actually in this orange box on the bottom left. It's saying that the knowledge base here consists of labeled examples of, and then objects, scenes, attributes, and relationships of 4 different types. So naturally, the first 3, objects, scenes, and attributes, are maybe something we've encountered to more or less of a degree in the course already. So the idea of storing labeled examples of objects, for instance, in a knowledge base, is actually more or less synonymous to the idea of core sets or the idea of just exemplar rehearsal, as we've seen in the forgetting lecture. So surely we could conceive the same thing in terms of scenes or attributes, depending on like the modality that we put in, making the knowledge base more than just the parameters, but figuring out that the memory buffer we've talked about when we have addressed catastrophic forgetting could also be seen as one form of knowledge. Now, what we've not really talked about is these 4 last things mentioned in this box, which is really the relationships of 4 different types, namely object, object, object attribute, scene object, and scene attribute. And what is meant by that is that, of course, rather than just storing an image or storing a piece of text and giving a label to it, saying that it's one particular type of scene or an object, we could also have a lot of auxiliary information on top, like relationships between objects, saying that the left object in the image is slightly smaller than the one to the right, and physical relationships, these kind of things that will likely be helpful if we want to have a learning process that capitalizes on these things and is maybe consistent with respect to specific physical rules, which is definitely from that point then interesting to have in a lifelong learner, but not something that's typically up to date talked about in the machine learning based lifelong learners. And so naturally, of course, this is primarily due to continuing machine learning than focusing on numerics. But it is arguably a frontier to now start to combine again the decades of really interesting research in AI with the also decades of really interesting research in machine learning. Of course, this is naturally now happening, and I hope it's also going to happen not only in things like causality, but also in directions like lifelong learning. So in that sense, as a summary, to go to our second example, to just illustrate on that further, knowledge is a lot more than just parameters, like we've said. And in fact, AI in more general is a lot more than just machine learning. And it's very likely that for lifelong learning and an open world, maybe machine learning at some point is not going to be enough. Let's take a look at the second example to just give you more of an idea of what it is that we can all do now if we really tap into this like pool of ideas from AI and machine learning. And it's this, again, almost like 7-year-old idea of the never-ending language learner. So I'm going to talk about it very briefly to end the lecture, because I really think that if you really want to appreciate this like large piece of software, it's been running for a really long time, 24/7, like multiple years, and accumulating knowledge, I encourage you to really look at it in detail, like read the respective publications, read the reports, take a look at the internet and the tool. There's some nice visualizations. But anyhow, I want to give you a really brief overview. So there are 5 plus 1, in a sense, elements to the never-ending language learner, or NEL for short, which is a coupled pattern learner, a coupled set expander for any language, a coupled morphological classifier, a rule learner, a knowledge integrator, and in a later version, the never-ending image learner we've just talked about. And of course, this sounds like a lot of buzzwords, so let's take a look at roughly what these different elements do. So the coupled pattern learner, or CPL for short, it learns contextual patterns, which means it's something of the sort of mayor of X or X plays for Y to, in a sense, extract categories and relations. And it's doing so by using co-occurrence statistics between noun phrases and contextual patterns. And based on these co-occurrence statistics, the relationships are used to filter out patterns that are like way too general. And so, like I said, I'm going to go on this like extremely generically and briefly, just to give you a sense of the possibilities that you'd actually have in ways of thinking about it if you really tap into this hybrid AI pool. The second element then is the coupled set expander for any language, which is, in a sense, really similar to what we've talked about in active learning. Like, it queries the internet with a set of beliefs from the categories and relations, and then starts to mine lists and tables to extract novel instances. It's doing so by like using mutual exclusion relationships to provide negative examples, to again like filter out overly general lists and tables. And somehow, and I'm going a bit on a stretch here because it's really potentially far-fetched, but if it helps your intuition, it's a bit like what we've said we could include like a negative form of knowledge, like our ideas of like known unknowns, for instance, into training when we've talked about like open versus closed worlds. Similarly, maybe from also a different perspective, also from the active learning inspiration for us, not for them, but maybe for us, but also for them, is the coupled morphological classifier, which is a set of binary logistic regression modules that classify noun phrases based on morphological features of different types. So it could be words, it could be affixes, it could be capitalization, part of speech tagging, and so on. And if you think of why that makes sense, it's a bit like what we've seen in model ensembles, but taken even further, where it's not just model ensembles trained on the same thing to get like a measure of uncertainty. It's in a sense like model ensembles on different pieces that describe the thing you're interested in, like the classification objective, to then later figure out in a bunch of slides that this helps us in figuring out what we should integrate and what we should not integrate. Most interestingly, I think, before we come to how this is all integrated, is in fact that, and this is something you'll not really see in the very numerical optimization machine learning literature, is that there's a rule learner. And the rule learner, it learns first order relational learning to learn probabilistic horn clauses. So if you have listened to an AI lecture, then you'll likely know that a horn clause comes from more of a like a logic perspective, and it's really going to tell you about like consistency in the sense of like logic. If A and B, then C. So you can use it to infer like new instances that follow certain relations that are consistent, without really going on this like very brute force numerical idea of having to form every prediction just by seeing data and optimizing on the loss with the target you have. But rather you could really go that like if something, if like A and B hold true, then also like C holds true, which allows you to have these like definite clauses to in a sense even ease the learning process, because you can capitalize on these constraints. And that's then useful if you think of the way that NEL actually constructs its knowledge base, how the knowledge integrator here works, which is really based or helped by this by these coupling constraints. So there are a bunch of mechanisms in place that allow you to construct a knowledge base in a way that's more holistic in that sense than anything we've considered so far. So naturally, there are also these ideas that we've talked about earlier, like maybe only integrate something that has a confidence from a single source with like more than 90% or so. Maybe also consider moderate confidence scenarios if like alternate classifiers agree in this ensemble. But particularly interesting here in L, it's about like respecting mutual exclusions, like disjoint categories, for instance. So if you know that you have particular like subsets and supersets, if you know that a motorbike is a vehicle, then it can't be a plane at the same time, for instance, right? So it's mutually exclusive, like either it drives on the ground or it flies in the air. It can't be both. And so if you learn a particular set of rules, a particular set of constraints about the related objects, about the supersets, you could derive them initially also for the concept you're now encountering and assume in the beginning that those are true, and maybe only then later figure out that there's a few things you need to change. So you can use really these couplings and these horn clauses to learn mappings that are consistent. And that's something that's quite interesting because it allows us to facilitate our training, to facilitate our knowledge-based construction, also keeping in mind that this form of knowledge, like relationships, is technically then not something that's as prone to catastrophic forgetting as parameters being overwritten by gradient descent are. Now I'm giving you, of course, this as like sort of the thing we should move towards. I do think NEL is a really interesting system, and like I said, you should take a look at it. I hope there'll be a version like 2.0 of it sometime. But of course, the version that is presented here has its own limit. One of them perhaps being the fact that once you have promoted or included a specific fact, a specific piece of knowledge, it never gets excluded again. So in that sense, it's limited because there's a view that you'll just accumulate knowledge over time indefinitely, which may not really be true. But it's also something we've thought of in the entire course as desired, where we've never really talked about the idea that maybe there are some things you should be forgetting over time. So maybe catastrophic forgetting sometimes is good. So I'm going to end the lecture today, and then you can, if you feel like you need to ask some questions or there are some unclarities left, you can ask them, but I'm going to end the lecture today a little bit earlier than usual on a quote. And this quote is from the NEL paper we've just talked about, and it is saying that we will never truly understand machine or human learning until we can build computer programs that, like people, learn many different types of knowledge or functions from years of diverse, mostly self-supervised experience in a staged curricular fashion where previously learned knowledge enables learning further types of knowledge, where self-reflection and the ability to formulate new representations and new learning tasks enable the learner to avoid stagnation and performance plateaus. So if you think of this quote and I guess almost this definition of lifelong learning, if you may want to call it that, then this is already more comprehensive than any of the other definitions we've seen before, in particular that it has many of the components we have talked about, such as avoiding stagnation and performance plateaus in the sense of forgetting. It's talking about staged curricular fashion in terms of curriculum learning. It's talking about learned knowledge enables learning of further types in the sense of transfer, years of diverse experience and mostly self-supervised experience. So in a sense of it's supposed to be supervision agnostic. But it also maybe goes a bit beyond a lot of the things we've talked about by formulating in the very first bullet point here that we should learn many different types of knowledge or functions, and not just in that sense parameters or data points as a memory buff that we store. So lifelong learning, hopefully as a frontier, just to summarize it, going from lifelong machine learning to maybe lifelong AI, and I guess AI or AGI in general should be lifelong almost by definition, is then about really leveraging all sorts of knowledge that we have, which is really the knowledge that we humans have in design and in terms of relations, not just in terms of parameters and data. And with that, I would like to thank you all the listeners who have joined in the live stream sessions and the team sessions, who have watched the recordings, for joining the course. Of course, also thank you for everyone who's going to watch this course later. And like I said, if you feel like there are some unclarities, this is a good video to post comments on or to include questions in the live chat. And otherwise, I'd like to just once more stress that the Continual AI community does have a Slack where there's a lot of discussion going on about recent papers, about this lecture, about anything that's continual and lifelong learning. So feel free to join there at any point in time by visiting continualai.org and asking your questions there then. Okay, as there are no immediate live questions today, I guess everyone's brain is melting just as mine is with 40 degrees and over 100 degrees Fahrenheit. Then again, I thank you all for joining, and I invite you to participate in the Slack chat, and you can feel free to follow up with all of your questions there.